You have seen that we often want to solve a matrix equation A times x is B. Wouldn't it be convenient if we could just divide by the matrix A? Well, unfortunately, it is not that easy. But we can do something else, called inverse matrices. Let us first start with normal numbers. If we have an equation ax is b and want to solve for x, you simply divide both sides by a, but only if a is non-zero. You can also see division by a as multiplication with the multiplicative inverse of a, which is 1 over a, or a to the power minus 1. The inverse has the properties 1 over a times a equals 1, and a times 1 over a equals 1. For square matrices, we take the same approach as for numbers. A square n by n matrix A is called invertible if there is an n by n matrix C such that C times A equals In and A times C equals In. If C exists, it is unique. So we can call C the inverse of A and denote this by a to the power minus 1, just like for the numbers. If C does not exist, you say A is singular. Let's try to find an inverse of the matrix A equals 1, 0, 0, 0. If C exists, it should be 2 by 2, so it would be of the shape PQRS. The product of C and A is P0, R0. If you want this to be equal to the identity matrix, you see that this can never happen because of the 0 at the lower right corner. This means that no values of P, Q, R, and S are such that C times A equals I. So A is singular. So you now know that matrices with non-zeros can be singular. Let us try another example together. The matrix A is 2, 5, minus 3, minus 7, and the matrix C is minus 7, minus 5, 3, 2. We can calculate A times C, which gives us 1, 0, 0, 1, which is the 2 by 2 identity matrix. Calculating C times A again gives us the identity matrix. So according to the definition of the inverse, A is invertible and the inverse of A is C. Now take a close look at A and its inverse. You can see that the inverse contains almost the same numbers as A. On the diagonal, the 2 and the minus 7 have traded places, while all other numbers are multiplied by minus 1. Might this be the same for every 2 by 2 matrix? With A given by AB, CD, and C by D minus B minus C, A, we can do the multiplication of C and A and arrive at a diagonal matrix with A times D minus B times C on the diagonal. So we still do not know whether A is invertible. You could, however, multiply C by the scalar 1 over A times D minus B times C, which will give you the identity matrix if you calculate C times A. In this case, you even get the identity matrix if you calculate A times C. Now we have found the inverse of A, and so A is invertible. You should, however, remember that we made the assumption that A times D minus B times C is unequal to 0 because you divided by this number. We can formulate the result from previous manipulations as a theorem. A 2 by 2 matrix A given by A, B, C, D is invertible if A times D minus B times C is unequal to 0 and has inverse 1 over A times D minus B times C times D minus B minus C A. If A times D minus B times C is 0, A is singular. Because A times D minus B times C is an important number, we define this number as the determinant of A. Now you know when a 2 by 2 matrix has an inverse. In class, we will tell you how you can use any inverse to solve equations, and even how you can find the inverse of any square matrix. See you in class.